Welcome to the second part of the series. If you have not watched the first part, then please watch the first part to understand the mathematical calculations based on what we are discussing. So the attention score is a number which tells each node how much it should care about its neighbor. So this is what all about attention score. So let's see how to do it. And let's take our example and consider feature vector of two nodes. So to calculate it, first we need to calculate two feature vectors. I know you are thinking why concatenate. Well, because we want to model to learn asymmetric feature-wise interaction between two nodes. So in our source node, if our source node is phone and target node is cable, then after concatenation it becomes like this. Okay, so you notice here WH of phone and WH of cable are the feature from our initial data. So from the previous slide we calculated concatenated feature vector, but does it tell anything yet? No, because those are linear. There is no non-linearity, right? So because if you have seen in the previous slide here, so here it's all linear calculation. So we are doing the concatenation and that's it. So so what we do, we introduce a learnable vector called A. And how can you do that? So this is just the matrix multiplication. So here we are doing matrix multiplication with screen different features. Now notice here that first part of the equation is the source node feature weight and the second part is the target node. Correct? So if we go back to previous slide, you can see these are the feature. This is the code snippet to do this. Probably you are asking why size it is 2 times of the output feature. Think about a bit. So the answer is well, because we always deal with two nodes, and technically we can have multiple nodes, but we are doing here pairwise attention. But in pairwise means it's two nodes, so otherwise we will not achieve the result that we are looking for. So that was the theory part. Now we see how mathematical calculation works and how to determine the score. So you notice here the different color indentation. You can follow the color indentation to relate to respective nodes. Okay. From our graph data, phone is connected to phone itself and then charger, battery and case. So here phone is the source whose index is 0 and it is connected to target which has index 0, which is eventually itself, and then charger which has index 2, and phone also connected to case which has index number 3. You remember that in the first data, in the first video we talked about that why we need the index. So here is what we need, the index. So the first column is source index and second column is the target index. And if you continue building the matrix, then it looks like for laptop like this. Again here source index of laptop is 1 and it's connected to itself again, and charger and battery which has their own index again. And if you continue to do so, then we get this matrix. I would suggest that you pause the video and go back to previous slide to check it. So now from the previous slide we have seen this data, right? So now if we map the index of rows from this table, then we get this. So for example, this is the row, right? And this is that thing which we are just taking the only row of the source. And now if we map the index of rows from the table that we get before, for example, if you go to the first part of the series, then let's go back here. So here if you notice here, so this is the table which we have got initially. And now if we come back and calculate the same things here, for 0 it's 0, right? And if we continue to building this, then we get this data. I hope it is clear that how I am building this tensors. Initially we had this data, and then based on the index for 0 0 these two, and again 0 0 these two, first force 0 is this, and then 3 times 1 is coming this one, okay, and then 2 2 2 again this 4 times this row, and so on. So moving on, similarly we need to do the same calculation based on the column index. So here initially we have seen in the previous one, this is the row and this is the target index, or this is the column index. And if we continue building this, then if we do the same calculation again, then we get this kind of data again. So what we have got so far is that source and target node embedding, which gives us the node edge feature. So this is the source index or the row index feature vector, and this is the target node feature vector or embedding, and then this is what we get, feature edge embedding. Now things get interesting. So we need to add a non-linearity for the model to learn unseen data, right? So why we need non-linearity? Because the model to predict the data based on the unseen data. So from previous step we got feature embedding, and we already have initial learnable vector A. If you remember, we have calculated based on some initial learnable vector, and which with this data now we can find raw data by doing matrix multiplication, and here is how. So notice here the row 0, and if you follow this row 0 here and multiply by first one this, and then this one multiply by this one, so at the end we get this value, this table or this tensor. So I have done it for a couple of nodes, so I would suggest that you can do it by yourself so that you get familiar with how it is happening, and then you will have more confidence. So as we have found out that learned data or signal from the previous calculation. Next we need to understand how important those signals are. So from now on we'll call it the signal, or the these are the raw data, we can call it a signal. So next we need to understand, as I said, how important those signals are, and this is where activation function comes into play. For this implementation I am using GELU activation, and it's one thing here I am using GELU activation. So one thing to notice here, some signals has negative and some are positive. For example, here the some score are negative and some score are positive. But those does not matter, means absolutely, because absolute value of the signal or the log gates only matters, only difference between them matters. So not the what the signal or this negative or it's a positive value, that does not matter, only the difference between them it's matter. So what we get here at the end, so once we apply this activation function, then we get this kind of a value, right? So, and the main purpose of this activation function is that it gives the signal as whether it's a strong signal or it's a moderate signal or weak signal. Again, the signal means how important the data is. So we can here I talked about only GELU, but there are other activation functions like leaky ReLU. Both of them has different purposes, and I will discuss about it later in this video series. So one important thing for you to remember here is that we have got these different signals. Now we need to filter out these signals. And why we need to filter out? Because we need to understand which signals are important. Some signals can be more important, some less, some weak. Okay, so this is the main purpose of this activation function. This means this, as I said, this absolute value of this log, it doesn't matter, only the difference between them do. And these are these things. Okay. So just a recap. So what we have done so far, that we have first we have learned the node embedding feature, then we did the concatenation, then we did single, we found out this, we did a dot with a to get the raw data, and then we put this raw data into activation function to get the nonlinearity. So meaning, in other words, how excited I is about J per pair. So in the concatenation we did this, how does it look when I look at J, but at the end of GELU it gives us how excited I is about J per pairwise whenever it is connected. So next part is softmax, and where we'll find it out that final attention weight, meaning how much percentage of X is how much percentage of node I listen to node J, and then how to update this score corresponding to each node feature. So that is more interesting part, and then that we are going to cover in the next video. So see you in the next video. Take care.